Hello, in this video we will discuss about some reactions and mechanism of addition reaction of alkene. Reactions of alkene. Addition reaction is the major type of reactions that alkene undergo. Now, to understand about the reactions and mechanism of this alkene, first of all, we need to understand little bit about the bonding in alkene. When we say alkene, like carbon-carbon double bond, alkene, one of the bond is, as we are aware that is a sigma bond, and other one is pi bond. And this pi bond is made by sharing of the pair of electron in the sideways overlap, by the sideways overlap. The pi bond is formed by the sideways overlap of the p orbitals. And because it is formed by the sideways overlap, this pi bond was somewhat weak compared to the sigma bond. As we know that sigma bond is formed by the linear overlap of the orbitals, whereas pi bond is formed by the sideways overlap. Therefore, pi bond are somewhat weaker. And because of this weak pi bond, these alkenes are somewhat reactive molecules. Because of this pi bond, these will be somewhat reactive molecules. And, and as you are also aware that this pi bond is nothing but the pair of electron. Therefore, this pi bond or this pair of electron will easily able to attack on the species that is deficient of the electron, or the efficiency that loves electron. Okay, so this type of species we call that as the electrophile. So this pi bond will able to react with the electrophile. And when this pi bond attack on the electrophile or electron loving species, that is when you will generate the electrophile will add to one of the carbon, whereas the other carbon will generate some positive charge. Okay, now on this positive charge, the nucleophile, some type of nucleophile, that which is a species having lone pair of electron or negative charge, the nucleophile will attack on the positively charged carbon. So this nucleophile will be added to one carbon, and electrophile is added to another carbon. That is how the pi bond will break and will generate two new sigma bond by addition of electrophile on one carbon and nucleophile on the other carbon. Therefore, this type of reaction we call as the electrophilic addition reaction. Electrophilic addition reaction. So the one most common type of reactions of alkene is electrophilic addition reaction, in which the electrophile will be added to one carbon and the nucleophile will be added to another carbon. And uh, other important point is this pi bond will break and generate two new sigma bond with the electrophile and the nucleophile. So in summary, the carbon-carbon double bond, if you add the species, say for example XY, say X is the electrophile, Y is the nucleophile, and carbon-carbon will convert into the single bond, and electrophile will be added to one carbon, nucleophile will add to another carbon. This is the type of the reaction that alkene undergo, and the name is electrophilic addition reaction. Now to discuss about the addition reaction, we will go with some specific example of such addition reactions of alkene. Now in this category, first reaction that we discuss is here, we call the addition of hydrogen halide. Hydrogen halide, also you can call that as addition of HX. Whereas the HX can be, it can be HCl or HBr or HI, right? So the X can be any halogen. Now, for this, let us start with the one simple example of the alkene, that is ethene, carbon-carbon double bond here. And now let's pick one hydrogen halide, for example, HBr. Now here, hydrogen is slightly positive and bromine is slightly negative. Yes, so hydrogen act as the electrophile and bromine act as the nucleophile. So as we discussed previously, in this process, the hydrogen will add to one carbon and bromine will add to the other carbon. Now, since this alkene is symmetrical, whether you add hydrogen to any of these carbon and bromine to the other carbon, you will have the same result in any case. So the result here is carbon-carbon will convert into single bond. Both are with hydrogens here. And hydrogen will add to one carbon, bromine will add to other carbon. This is the result. Double bond convert into single bond. And the mechanism, we can simply explain this mechanism as discussed previously. Carbon-carbon double bond. Again, you got to learn how to draw the arrows in this type of mechanism. Again, HBr, so hydrogen is slightly positive, bromine is slightly negative. Double bond, this is a pi bond that we are using, will go and attack to this slightly positive hydrogen, which is acting as the electrophile here. Once it grabs this hydrogen, this bromine will leave as the negative. So the result here is carbon, since you have used this pi bond, it will convert into the single bond, and hydrogen will add to one of the carbon. So it can be any carbon, either of this carbon. So for this case, let us add on this first carbon here, so that the second carbon will generate the positive, or carbocation is generated. Now, in which this Br minus as a nucleophile will attack on the second carbon here, as will attack, and the result here is CS3 and CS2 now will add bromine here. So that is how you get ethyl bromide as the product. Now we can give varieties of such example. There's, let's say for example, here we add again the cyclohexene. Now suppose we are adding Hi to this molecule. So across the double bond, one carbon will add hydrogen and other carbon will add iodine. So the result is very simple here. Hydrogen, and this is a symmetrical molecules, which goes where is not important here. So hydrogen to one carbon and iodine to other carbon. Double bond is converted into single bond. These are some examples of addition of hydrogen halide. But the problem comes when we are adding this hydrogen halide to some unsymmetrical alkene. So if it is symmetrical, does not matter whether you add hydrogen and iodine to which carbon, it is not an issue there. But if we are using unsymmetrical alkene, then we have, when you have the regioselectivity. Regioselectivity, that is what we wanted to discuss, regioselectivity of addition reaction. Now for this, let us take the example of an unsymmetrical alkene, one simple unsymmetrical alkene. Say it is propene, 1 2 3 carbon, so it is propene, and we wanted to add HCl to this alkene. Now in this case you have two possibilities. Okay, so one possibility, if we add this hydrogen to this terminal carbon with the two hydrogen there, and chlorine to this carbon, say this is path A, then we will have the product. Hydrogen is added to this carbon, the terminal carbon, and chlorine is added to the middle carbon. So this is the case when you have here 1 2 3, that means 2 chloropropane is the product. Now, if we add the other way around. That means, say, hydrogen is added to the middle carbon and chlorine is added to terminal carbon. Then the result will be, so hydrogen adding to this carbon in the middle carbon and chlorine adding to terminal carbon. So it will be 1 chloropropane is the product in this case. Now the question is, which one will be the major product? So how does the addition reaction takes place in such unsymmetrical alkene, right? So this we can explain very clearly by, if we follow through the mechanism. Let us discuss the mechanism, how that two possible product is happening, and we can understand which one will be the major product in that case. Okay, so see that carbon-carbon double bond, we are adding HCl across the double bond. So hydrogen is slightly positive, chlorine is slightly negative. As we discussed previously, this double bond will grab this hydrogen, slightly positive hydrogen. So if it is following path A, then the hydrogen is added to the terminal carbon. So you have hydrogen adding here, and you will have the carbocation generate on the middle carbon. So this is following path A. And the Cl minus obviously then will attack on the next step, will attack on this carbocation, will generate the product A, that is with the 2-chloropropane. So 2-chloropropane will be the product. That is in path A. If we look at the follow, if we follow through the path B, then what happens here? The double bond will grab the proton, and then proton will go to the middle carbon, and you will generate the carbocation on the terminal carbon. And now Cl minus will attack on the terminal carbon. The result will be the formation of the 1-chloropropane as the 1-chloropropane as the product, 1-chloropropane. Now, if we closely look at this intermediate carbocation, so in path A, the carbocation generated here is what? Secondary carbocation, whereas in path B, the carbocation generated is primary carbocation. This one is secondary carbocation, and this is primary carbocation. And you all are very familiar about the stability of the carbocation. Tertiary is far better than that of, this is the carbocation stability order. You cannot forget this. Tertiary is far better than secondary, better than primary, better than methyl. We have studied that in previous chapter. So based on that, secondary carbocation is much more stable than that of primary carbocation. Therefore, this path A will be followed. Resulting product will be 2-chloropropane. And actually the path B, that will not happen, because primary carbocation is so unstable, then this will not form. Therefore only the path A or 2-chloropropane will be the result. Now with this we can have the general idea. We can discuss this idea as what we call is the Markovnikov rule. Markovnikov rule. And based on this rule, okay, so whenever we are adding alkene and hydrogen halide to add to this alkene, for example, then according to Markovnikov rule, the hydrogen or the positive part will go to the carbon containing larger number of hydrogen, and the halogen will go to the next carbon. So this terminal carbon has 2 hydrogen, whereas the middle carbon has only 1 hydrogen. So the hydrogen of hydrogen halide will go to the terminal carbon. So the result here is hydrogen will be added to this carbon on the terminal, and iodine will be added to this carbon. This is what we call the Markovnikov rule, right? Markovnikov rule, and this rule is a very popular one, will be followed there. Now see, for example, other one here, if you add hydrogen bromide